I to the power of I is actually a real number. This seems counterintuitive, as we have the imaginary unit raised to the power of the imaginary unit, but end up with something real, and not just a normal real number. It is this odd-looking decimal number. You must think I'm completely crazy, but let me prove this to you. First, we need to look at the natural logarithm. It is the inverse of the exponential function, and therefore, it has these identities. We will start by using the first one, by writing it with I to the power of I like this. We then use the log power rule and can take out the I. Now we have hit our first problem. We need to figure out what the natural logarithm of I is before we continue. I is the imaginary unit, and we use this to form complex numbers. We usually call a complex number z, and it is defined as a plus bi. It therefore has a real and an imaginary part. I in itself is a complex number with no real part and an imaginary part of one. Our problem here is therefore to figure out what the natural log of z is. Since a complex number has a real and imaginary part, we can plot it in the imaginary plane like this. There are also other ways of representing this number, for example, in the polar way. Instead of using a and b, we can use the length r and the angle theta. To write the polar representation, we need to remember what the definition of sine and cosine is. They are defined like this. We can isolate the sides of the triangle by multiplying with the hypotenuse. Relating this to our triangle, we get these expressions. We can then put these together to form the complex number. Now we notice something amazing. Inside the parenthesis, we actually have Euler's formula. So we just simplify and get the polar form of a complex number. So far, so good, but we wanted to know what the natural logarithm of z is. Let's plug in the polar form we just derived. Since we have a product, we can separate. Now we need to go back and remember the second identity of the natural logarithm. It shows us we can just write I theta. All right, we now know what the natural logarithm of a complex number is. But we needed to find specifically what ln of I is. To do this, let's plot the complex number I. As I stated before, I is a complex number with no real part and an imaginary part of 1. We can see that the length is 1 and the angle must be pi over 2. Let's plug this in to the definition we derived, and we get ln of I equals ln of 1 plus I times pi over 2. We can immediately remove ln of 1 as this is just 0. We can now return back and plug this in where we left off. We therefore get e to the power of I times pi over 2. Two i's multiplied with each other just gives -1, so we end up with e to the power of minus pi over 2. If you put this into a calculator, you get the crazy decimal number. Please don't forget to like and subscribe.